Okay, good evening. I was giving people some time to log in. So, welcome to the Arizona Arc and His Society lecture for September 2025. Today, we have the pleasure of having our president, Eric Kuklas. He's going to give an opening speech for everybody. Uh, and then Dr. Gary Huckleberry is going to present his lecture. So, Eric, please go ahead. The screen is yours.
Okay, thank you, Sebastian. Hello, my name is Eric Klukas, and I am the sort of new president of the Arizona Archaeological Historical Society. I've been in the saddle now for a couple of months, and I am going to be very quick. It's going to be not much of a speech, but there are a couple of things that I would like to bring to everyone's attention. First of all, and most importantly, thank you for your attendance. We've got my understanding is we got a fairly good crowd tonight, for which I'm sure is going to be a very interesting lecture. We have a couple of changes in the works for the lectures moving forward that you will notice maybe in the next, if not next uh, month, the month after, is that we're making a transition from using Zoom as our remote platform to Microsoft Teams. That will, for the people coming into the lecture, it will there will be very little change. You don't need to have teams. People that it'll be very similar to what we have now. Is you'll receive a link to the talk. You register for the talk. You click on the link, and then you enjoy the lecture. Something that we're moving towards that is going to take a little bit more time, though, is we are making a concerted effort to return, at least in part, to in-person meetings. This is something that, of course, prior to the pandemic was the standard format for these lectures. It's something that several years ago, 2004, 2006, was my first round on the board. That was one of the things that we look forward to the most, was getting together once a month over at the Duval Auditorium for the talk. And at the time I was the vice president for activities, and one thing that we did was take the speaker out to dinner at Casa Molina, which is also something that I miss. That hopefully we can resurrect that. We plan to continue with the Zoom/Teams based lectures in addition to the in-person meetings. I think that some of the advantages of the remote meetings is worth continuing. People who are not in Tucson and can't get down to Tucson for the lecture would still be able to see the lecture. It would broaden our the potential pool for presenters as well. People that, again, cannot get to Tucson but are interested in presenting. So that is something that probably after the first of the year, we're going to have a couple of trial runs internally. And after the first of the year, there will be that option will be available. And I hope that this is something that people are interested in, and we can return to the more social aspects of these meetings, which was always something that I appreciated, and I think that a lot of people enjoyed. So again, welcome, and I will then now turn it over to Sebastian, who will introduce tonight's speaker.
Thank you, Eric. Hello again. Like I previously mentioned, I'm Sebastian. I'm the co-vice president of activities. Uh, and today I'm honored to introduce Dr. Gary Huckleberry, uh, who's going to give us his presentation on soil degradation in the Hohokam in the Phoenix Valley. So, one thing before I hand it over to Gary, uh, we're going to have the Q&A session at the end of his lecture. So you can type the questions on the chat portion of the Zoom at any time you want, but he's going to answer them at the end of his lectures. So here he is, Gary Huckleberry. Please take over. The screen is yours. See you at the end.
All right. Thank you, Sebastian. And thank you for all of those who are signed in tonight to listen to this presentation. Some of you know me, some perhaps don't know me. Just to give you a little background, I was born and raised in Phoenix and started working in the 1980s, late 1980s, doing contract archaeology as a geoarchaeologist. I'm trained as a geomorphologist with a specialty in soils, but I apply it to archaeology. So I was doing geoarchaeology full time in the 80s and started looking a lot at Hohokam canals that were still preserved beneath the city of Phoenix. And I was really interested in how centuries of irrigation and redistributing water on the landscape affect the environment through time, and how that environmental change impacted the Hohokam as well. Well, fast forward 40 years, I'm still out there looking at these canals and looking at how they might impact soils and thus my talk tonight. The title of my talk is somewhat provocative because it implies that soil degradation drove Hohokam decline in the 15th century. That was my hook to get you to attend my 45-minute slideshow on dirt. So I'll say from the start that I don't believe soil degradation led to the decline of the Hohokam. I think there were several factors that were impacting the Hohokam during the Classic period, social and environmental factors. And in some places, I think irrigation did result in the degradation of soils, which limited food production. But in other cases, in other locations, prolonged irrigation did not seem to be a problem, and that is the agriculture was sustainable. So, in an effort to better define the environmental context of Hohokam decline in the late Classic period, I think it's important to sort of review what are the impacts of prolonged irrigation on soils and how that might have impacted the Hohokam. So I will go to screen share and start my talk. There we go. All right. So tonight I'm going to we'll revisit this idea of centuries of irrigation perhaps degrading soils and leading to societal stress, with a focus on the Hohokam in central and southern Arizona. I'll start by just doing a brief history review of canal irrigation in Arizona. It's a deep history that predates the Hohokam by quite a bit. I'm going to also just review desert soils and how they're modified by irrigation. If we're going to try to identify these human modified soils in the landscape, we need to know what do the natural soils look like. So I'll do a little bit of desert soil morphology. And then I'm going to give some examples of work done by many of my colleagues and some of it by me on some where we have examples of positive and negative impacts of irrigation to soil. And then talk about the potential impact of soil degradation on Hohokam settlement, focusing on the Salt River Valley. And then I'll touch a little bit on recommendations for future work. So as many of you know, yeah, we have a deep history of of agriculture in the Southwest. It goes back almost 5,000 years. And we have at least 3,500 years of canal irrigation agriculture, which is it's incredible. And these early canals that were built 3,000, 3,500 years ago were pretty small. This was a time when people mixed agriculture with foraging. Some would argue they were more foragers than farmers, but it was a mixed sort of foraging farming lifestyle. But through time, the canals got bigger. Canals are a hallmark of intensive agriculture, where more effort, more work is put into the landscape, diverting water to grow crops, resulting in greater productivity, greater caloric output from your farming. And this facilitates increases in population growth, particularly with the development of ceramics where food could be stored. And through time, guess what? Canals got bigger, and there was a greater impact on the landscape from irrigation as these canal systems became larger. So one could argue that the zenith of these ancient canal systems occurred in the lower salt, middle Gila River valleys at the time of the Hohokam, where you have hundreds of miles that were constructed over multiple centuries. And these canals influenced not only subsistence, but population and social relationships and where people place themselves on the landscape. And now the scale of these earthworks, the scale is monumental. But yet these were not state level societies. At least most do not believe the Hohokam attained state level political organization. Instead, they relied on a more loosely structured distribution of power and cooperative organization. That in itself is interesting because that kind of goes against some early ideas of you have to have high levels of political complexity to build monumental hydraulic infrastructure like this, but apparently not, at least not in Arizona. So this is a map of some of the canals that have been mapped, let's see, in the lower Salt River Valley. And this is a plot of what we know of Hohokam population. This is an estimate based on the archaeological record, which is never, which is always has some limits, undoubtedly. But generally speaking, we see an increase in the pre-classic that sort of the population peaks in the AD 1200s. And in the lower Salt River Valley alone, estimates 20 to 40,000 people living there, which is arguably the most concentrated population in what is today the U.S. Southwest prior to Spanish contact. Now, the valley and beyond the valley witnessed demographic decline beginning in the 1300s. And by 1450, what we know as Hohokam, as defined archaeologically, is gone. And as most of you know, this demographic decline was a regional phenomenon. It happened throughout much of the Southwest, and it involves societies that were not reliant on canal irrigation. So you can't invoke degraded soils for this regional demographic decline. Obviously, different social and environmental factors were probably at play. We're still trying to work on that. But in terms of some of the environmental processes, one idea that periodically gets attention is the soil salinity hypothesis. That is the idea that after centuries of irrigation, these Hohokam irrigated soils just accumulated salts that precluded the ability to grow crops, creating food stress, and then led to this demographic decline. So that sometimes known as, like I said, the soil salinity hypothesis. Now, this hypothesis goes back probably the 1920s because at least in the lower Salt River Valley, many of the historic farmers were already having problems with waterlogged soils and salt buildup. And by like the 1920s, already a quarter of the lands that were irrigable were fallow because the soils were too waterlogged and built up with salt. And so that got some of the early archaeologists thinking, well, maybe the Hohokam had that problem. And then later, research in the Old World, particularly Mesopotamia, where we had evidence of there where irrigation over centuries, if not millennia, really salinize the soils. We actually have records on clay tablets in the Tigris-Euphrates Valley where crops went from salt tolerant to, salt intolerant to salt tolerant, lesser quality grains like wheat to barley. So these things got archaeologists thinking about, well, maybe this happened with the Hohokam. And then in the 60s and 70s, we sort of swung away from sort of environmentally deterministic explanations of culture change. And then locally, a paper was published in Kiva by Neil Ackerley, which really kind of gave a good argument that why it's unlikely the Hohokam decline was tied to soil salinization, based in large part because historically soil salinization occurs on the orders of decades, and you had 1,000 years of Hohokam canal irrigation in the lower Salt River Valley and other places. So it seems like the timescales are off for soil salinization to have been a problem. So you didn't hear much about the soil salinization hypothesis until a few years ago. A paper was published by Henry Short in the Journal of Environmental Quality, where he argued that indeed, in the lower Salt River Valley at least, soil salinization continued gradually until it reached a threshold in the classic period. And that was something combined with, he argued that the tree ring record suggested reduced flooding in the 1200s, which that those floods leach those salts out. That combination of sort of cumulative salt buildup, reduced overbank flooding, that was the 1-2 punch that sort of led to the collapse of the Hohokam. This was followed by a rebuttal by Chris Castledine at ASU, who really kind of showed nicely that given the variety of different soils, the diversity of irrigation techniques, and just the mobility of fields within the lower Salt River Valley, the dynamic nature of these canal systems, it's unlikely that soil salinization caused the Hohokam decline. So this whole idea of soil salinization and Hohokam decline, it's still out there, thus giving me an opportunity tonight to talk dirt with you, which is what we're doing. So before I begin getting into the details, just want to review a few terms. One is soil quality. When I talk about, when you say soil quality, that's a positive thing. That's the ability of soil to support life. It's the physical and chemical properties that allow it to function and sustain ecosystems. In an agricultural context, we might use the term fertility because it allows for the production of crops. The opposite side of the story on that is soil degradation, all right, where we have soils that might be compacted. You might get reduced soil structure and aeration, which limits the ability of plants to absorb nutrients and water. Or you can, through time, in an agricultural context, you get nutrients depleted because of repeated harvesting of crops. You might get concentration of salts due to prolonged irrigation, and that creates problems with water nutrient uptake. And all these can contribute to enhanced erosion and loss of topsoil, such as what we see here on the picture on the right. So on two ends of the spectrum, soil quality good, soil degradation bad. The idea in terms of soil salinization is one type of soil degradation. Okay, so if we're going to try to understand how agriculture and irrigation in particular impacts these soils, we kind of know what they look like. Now, most irrigation agriculture takes place in drylands. And dryland soils or desert soils, here in North America, we often refer to them as aridosols. They have certain properties that are quite different from, let's say, soils in more humid climates. Desert soils are really driven by the dry climate, the lack of vegetation, inputs of dust. So we get these very unique looking soils. They don't tend to have dark, rich, organic A horizons. They tend to get salts building up in the soil through time. And, soils are these dynamic living things. They're a mixture of geology and climate and biology. And if you have a soil as a living entity, the older that soil is, you'll see more changes in that soil. So this is a perfect example. Here's one soil on my left, 10,000 years old, soil on the right, million years old. Same parent material, same environment. They're 25 miles apart. This is in southern New Mexico. The one on the left starting to get a little bit of salt buildup in the soil near the top. In this case, calcium carbonate. On the right, that carbonate has made a caliche horizon, cemented solid. And then also you get the iron oxides up top, you get that red orange. So, these are the type of soils the Hohokam were facing when they were irrigating, certainly, excuse me, when they were bringing water outside the floodplain. Now, in the floodplain, desert soils, there are exceptions to the rule about not having much organic matter. Most desert soils have less than 1% organic matter. But in floodplain settings, particularly fine-grained floodplains, you can get organic matter contents that are much higher. And by the way, most agricultural soils have more like, excuse me, 5-6% organic matter content in the topsoil. So in terms of desert floodplain soils, we have to consider where in the landscape we are, or excuse me, desert soils. And in floodplains, fine-grained floodplains, you can get these fine-grained organic soils, which are actually pretty darn good for growing crops because they've got important nutrients like nitrogen and phosphorus, and chances are you're close to a water source where you can irrigate. Now, the drawback of doing farming in a floodplain is water tables historically were shallow in a lot of these desert floodplains. And irrigation farming, canal irrigation farming, risked raising those water tables even higher into the root zone where salts can form. So if you can imagine some brackish groundwater, such as this picture on the left, and near the root zone, and with the evaporation and transpiration at the surface, the plants are bringing that water up. That water evaporates, those salts go out of solution and concentrate in the root zone, and that's going to limit the ability of the plants to obtain both water and nutrients. And, depending on the tolerance of the plant to salt, it could kill the plant. So that's the one drawback of farming in these floodplains, particularly the fine grain ones. They're prone to shallow water tables and then waterlogging and bringing salts to the surface. And by the way, not all salts are equal. Some salts are more deleterious than others. For example, sodium salts will not only limit nutrient uptake, but also will modify the soil structure by dispersing clays and creating somewhat of an impermeable layer in the top, which further leads to compaction and soil degradation. So sodium salts in particular are very harmful to farming. So as mentioned earlier, that in the lower Salt River Valley, a lot of farmers were having problems after a few decades and could not farm. Here's a picture looking south from Tempe Butte in around 1900. And you see some fields that were left fallow. Farmers are not farming them at that time because they are encased in salt. Now, these are the same soils that the Hohokam farmed. In fact, if you dug a trench into those fields, you'd probably hit Hohokam canals in the subsurface. So again, this led many people to think, well, maybe the Hohokam had problems with salinized soils, just like the historic farmers did as well. Okay, well then let's consider exactly then how might ancient irrigation impact these natural desert soils, and it's more than just salinization. There are other impacts that could be deleterious as well. So this gets back to, what it is that canal irrigation does to a soil, a natural desert soil. Basically, you're transferring water and sediment. That's important. It's not just water, it's also sediment from where it would naturally go, down a river or stream, onto the landscape. And in the case of canals, the sediment's going to go down the canals and into the fields. They'll collect in the canals, they'll collect in the fields, and through time you get this buildup of sediment. And particularly at the distal ends of the canal systems and in the fields, you get these fine grained silts and clays building up through time, so the soil will thicken through time. And we actually have a term for this type of over-thickened clay-rich soil. We call it an irragric anthrosol. That's a mouthful. Say that 3 times real fast. Irragric anthrosols, and they're common to desert environments. And we see them on the landscape today. They're caused by modern farming, but we actually have irragric anthrosols caused by the Hohokam. Irragric, irrigation, anthrosols, human produced soil. All right, so these are some different types of field systems you might have. This is from an old publication by Fred Niles and Dave Gregory. The structure of the field systems will vary with topography, but in all cases, you're going to get buildup of sediment through time by repeated irrigation with muddy water. All right, so if that's the case, if you're getting the deposition of fines, where might that process improve soil quality? Well, one is not in so much the fine-grained floodplains along the axis of the valleys, but on the margins, where some of the tributary streams come into the valley, where soils are naturally porous, where the deposition of silt and clay would actually improve soil quality. And this is something that we see in the northern Phoenix Basin and eastern Phoenix Basin, where the Hohokam were diverting water off of seasonally flowing streams like Cave Creek and producing these silt-enriched fields. Now, these fields were documented by several of my colleagues, Bruce Phillips and Hosky Shafsma and John Briggs. They published on this. I got a chance to look at some of these. The picture on the left shows some of these silt fields in black along the edge of Cave Creek. It's one on the right. Now the circles here kind of show what you might see these actually still on aerial photography. The one in red is one that I got to work on because they built Sonora Boulevard there in North Phoenix, and it went right through this silt field, which was fortuitous for me because we got to dig into it and see what it looked like. And what we have is something that's about 1,450 feet in length and about 500 feet wide and about 3 to 6 feet high. It's a big deposit of irrigation sediment that sits on coarser soil. Excuse me. And these sediments are nutrient rich. They carry nitrogen, they carry phosphorus. They create this fine matrix in these coarse soils that allows the soil to hold on to water. There's this plasma. And so, we were able to trench through there and date this. I mean, we've got a canal that comes in and feeds it on the north up on top. And then pottery associated with this, we think it dates to about AD 1000 here at Site 30. Now, again, this is an example of how you modify the soil. The one on the left is what the natural soil looks like underneath. Not exactly ideal for growing corn, very marginal agriculturally. On the right is the silt-enriched soil, about a meter thick at Site 30. So again, that's that fine-grained plasma, which really helps with holding moisture and allowing for nutrient exchange with the roots because of the finer particles in the soil. Now, irrigation, agriculture by itself, canal irrigation will deposit the sediment, but here on these silt fields, it looks like the Hohokam made an effort to accelerate the sedimentation by creating barriers to the either flood water or the canal water that was being distributed. So we get these rock alignments on and in the silt fields, and we think that these are features probably associated with vegetation that were designed to slow down the water and drop the sediment. We know ethnographically the Odam did this, the Danatam did this in the Papagoria, and we know that, well, still today in northern Mexico, we still see these living fence rows capturing runoff and diverted water from rivers during the summer monsoon to help capture sediment and find sediment to facilitate crop growth, agriculture. So that's an example on the margin of the Phoenix Basin. Here's an example where we think Hohokam irrigation improves soil quality, and this is in a place where you wouldn't expect it. This is along the Middle Gila River on the Gila River Indian Community. So in this area, soils are naturally fine-grained, and this is an area where we have some long-lived agriculture, and particularly here at the Snaketown system, we've got a canal system that was irrigating for several centuries. And what's even better about this situation is, unlike most places in the Salt River Valley, you have Hohokam fields that have not been subsequently cultivated and irrigated, so that you have what we might call pristine soil situation there. And again, people lived in Snaketown for centuries. It was fed by this main canal whose intake is near Gila Butte there in the lower right, near where I-10 crosses the Gila River right now, and which is currently under construction. If you've driven up to Phoenix, you've probably seen that. So the Gila River Indian Community, the Cultural Resources Program led by Kyle Woodson, he collaborated with soil scientists John Sander and Colleen Strawhacker in a soil investigation here to see how that long period of irrigation affected soil quality. And so they actually dug one of these fields implied from at the distal end, applied by the canals, to look at the soil and see what the physical and chemical properties are and compare that to some of the natural soils around there. So let me get a picture here what that looks like. Picture on the left is the actual soil profile. This is the irragric soil up on top. It's about 70 centimeters, 3 feet thick, overlying the natural soil underneath. Here's on the right is a map of the different soils that have been mapped in a Snaketown area with the canals. What they discovered is that this soil actually did have moderate levels of sodium, which would have been harmful for some salt-tolerant crops. So you might think, aha. But when you compared it to the natural soils outside the irrigated areas, salt levels were actually lower than the natural soils. In other words, irrigation here actually improved soil quality because the soils were naturally salinized and sodium rich in this area. So it did, you got an irragric soil building up through time, and they probably did have problems with sodium to the point where maybe, you know, some salt intolerant crops, it might have been problematic, but overall, it seemed like they were able to manage the problem because they farmed this area for centuries, obviously evidenced by this thick irrigric soil, and were able to somehow deal with the problems of salinization. So here are a couple examples then of irrigation improving soil quality. Let's look at the other side of the spectrum, where irrigation might actually degrade soil quality. And the example I start off with here is not one that you typically consider with irrigation, agriculture, irrigation impacts of soil. Here I'm going down to Tucson to look at an early agricultural site, Las Capas, where excavations there over the years, and particularly by desert archaeology, you know, revealed these pre-Hohokam, pre-ceramic, early agricultural fields. And in several of these fields were these deep cracks originating from the surface of the fields down into the subsurface that were filled in with sediment, but they were former cracks, or what we know as what we call soil pipes. The process is soil piping. Excuse me. So soil pipes are a subterranean erosion feature whereby surface water infiltrates quickly down through cracks and tunnels, and then eventually will erode and get larger and larger. Next thing you know, you have these large vents that then collapse upon themselves. And if unimpeded, you know, it will just completely result in a perforated sort of agricultural surface. It's a natural process. It occurs in floodplains, fine-grained floodplains, areas of gypsum-rich soils. But at Las Capas, we actually have it associated with these early agricultural fields. This is just a picture showing you a collapsed soil pipe. In this case, the one on the left, Laguna Pueblo in New Mexico. The diagram on the right gives you an example of how these things occur naturally, not just in floodplains, but actually on hill slopes as well. So it's a natural process, but at Las Capas, it appears that it was aggravated by irrigation, and particularly the irrigation sedimentation, the deposition of silt and clay in the field. So picture on the left shows these early agricultural field cells. These date about 1000 BC. They look dark. They're outlined in white. They're darker because they have this darker clay in them from the irrigation sediment. The picture on the right is actually one of these large collapsed soil pipes originating from the surface of one of these fields. So again, any effort to irrigate this area, once these soil pipes would form, it disrupts the ability to get water to your fields, and it can lead to further erosion, rill and gully erosion. The good thing is these things heal fairly quickly, and at Las Campas, a couple human generations later, it appears that they resumed canal irrigation and farming in this area. But at human timescales at the time, it can be quite disruptive, and so it's another example of irrigation degrading soil quality. So perhaps the best evidence of desert soils being negatively impacted by ancient irrigation is found along the lower Salt River. And going back to the first soil survey of the valley, done in the turn of the century, late 1890s, early 1900s, a guy named Thomas Means identified this soil he called Salt River adobe. And it's very thick, very clay, dark, and as he was mapping this soil, he noticed it occurred next to prehistoric canals. Now, at the time, a lot of those canals you could still see at the surface, even in areas, even in plowed up fields. Excuse me. And he hypothesized that the soil was formed primarily by repeated prehistoric irrigation with muddy Salt River water. As far as I know, this is the first mapped anthropogenic soil in the United States, where the soil is so extensive, it's actually a mapped soil type. Now, earlier I mentioned historic waterlogging and salinization problems faced by early historic farmers in the Salt River Valley. Um, those areas of salinization were commonly associated with the Salt River adobe. It was a problematic soil. Here's a typical picture of the Salt River adobe in a backhoe trench. This was about a half-mile south of downtown Phoenix. Typically, it looks like this. It's dark brown. It's clay. It's got really well-developed structure. The upper part is plowed there, and that's very typical because these soils were farmed historically. In terms of where they're found, here's a map by Brett Hill and colleagues that shows where Means mapped the Salt River adobe in the Salt River Valley, and then also the canals superposed upon that. A couple things stand out. One is that the Salt River adobe is generally located close and parallel to the Salt River. The two main exceptions are in, let's see, central Phoenix here, where it comes out of the floodplain onto a higher Pleistocene terrace, and then south of Tempe, kind of like that picture we saw looking south from Tempe Butte earlier. The other thing is that there's still a lot of area covered by canals that don't contain Salt River adobe, but I will put in the caveat that Thomas Means did not survey the whole valley. So like this area in the southwestern part of Phoenix has Salt River adobe, but it just isn't mapped. But nonetheless, the canals certainly extend beyond the range of Salt River adobe, and that's important to notice. Now, people started, I should say Salt River adobe as a soil name is no longer used. It was later replaced by other terms like Pima clay, Cashion clay, terms that the then Soil Conservation Service and now the National Resource Conservation Service used for these soils. But you can see that some of these soil patterns, and these, particularly the ribbons, really match closely to Hohokam canals. This is something Al Dart showed in a publication also in Kiva back in the 80s, where this is some of the Hohokam canals in Canal System 2 in Central Phoenix. And you can see how some of these soils, like the Cashion clay, match closely to these canals. So even beyond the Salt River adobe, there are these other hints that some of the modern soils that we have really are related in part to ancient irrigation. I had the opportunity to work with some of these soils in the late 80s as well in the urban core of Phoenix, where I wanted to show that the physical properties in the soil, even though they weren't really visible, if you looked at it at a fine grain or fine scale, physical properties changed in relationship to the canal. So in this case, a prehistoric canal buried by a plow zone, historic plow zone, did a long trench and sampled the soils away from the canal and saw progressive changes in texture that weren't real visible in the field, but at least with lab data, you could see sand decreased away from the canal, clay increased away from the canal, probably related to canal cleaning and then slope wash away from the canal. The point being that despite historic plowing and all these other disturbances, you still had physical properties in the soil that could be linked to ancient irrigation. So now, moving forward in time, I had the opportunity to be part of an investigation near Sky Harbor Airport with desert archaeology, where we were able to come across the Salt River adobe in a very unusual setting, and that is one where it was buried by a Salt River flood deposit and never historically plowed. So it was, quote unquote, semi-pristine. It wasn't plowed, although it had been irrigated historically, and thus the chemical profile was modified. But the physical aspect of the canal was intact. And it was located next to a palimpsest of main canals in what we call Canal System 2, Hohokam canals that were built over several centuries. So here are a series of canals. Here was where the Salt River adobe was. In this area here were a series of habitation structures, intramural features that provide an opportunity to date the soil that were embedded in the soil below, in, and above. So we took advantage of this opportunity to look at empirical data, empirical evidence from that soil that might show that it is indeed an irragric anthrosalt. It was formed by irrigation agriculture. Because we're still in the Salt River floodplain here, it could have been formed naturally by overbank flooding, much like those natural fine-grained floodplain soils I showed you, but just happened to be near Hohokam canals. Well, to show that it is indeed anthropogenic, we looked at various physical and chemical properties, and we decided to look at micromorphology and pollen in the soil. And with that, I was helped by Louise Perdue, who's a soil micromorphologist, and then pollen, Susie Smith, looked at the pollen. And here's a look at what that soil looks like. These are some of the soil horizons that we broke out in the soil. It's about 70 centimeters thick, about a little over 3 feet thick. The BW horizon over here, this is the soil, this is the flood deposit that buries it. This is the soil. And we sampled it both in terms of bulk sediments and blocks of sediment so that we could do micromorphology. In terms of the micromorphology, a lot of things that Louise identified really indicated or suggested that it was an irragric anthrosol in terms of a lot of fine dispersed charcoal, large organic particles within it that are common to agricultural fields. And also things that are quite interesting. Also fine lamina suggesting repeated irrigation, slow energy irrigation, or deposition of sediment that's consistent with irrigation. And then also was interesting is these phosphorus halos on some of the soil particles, which suggests fertilization. And that's rather interesting because, one, we don't have large domesticated animals in pre-contact Southwest. And it's not documented ethnohistorically. Now, to really demonstrate that this is fertilization, we would need more biochemical evidence. But the micromorphology, these phosphorus halos, are not typical of natural soils or floodplain soils, and so suggests perhaps the Hohokam were fertilizing their soils. Susie identified pollen, and guess what? Maize pollen throughout it. So that was good. Again, suggesting the irragric origin. For terms of dating, Kathy Henderson had these wonderful ceramic radiocarbon dates, which brackets this soil from AD 700 to 1200. And what we see is what we expect from irragric anthrosol: increases in clay through time. Over here, silt and clay through time. Organic matter increases through time, total organic carbon, total nitrogen. These would be good for soil fertility, but this not so much, because this is where the soil gets so thick and so heavy, it gets difficult to work, and it makes it more susceptible to waterlogging and salinization. We looked at some measurements of soil salinity, electrical conductivity, sodium absorption ratio. It suggests that there might be some salt issues, but the problem is this soil was historically irrigated, and salt content is very labile. It's very prone to change, and so the soil, any sort of soil salinity signature we see in that soil, even though it was never plowed, is probably historic. And so it's inconclusive in terms of soil salinity. But certainly the thickness and the water locking, it seems much more credible. And thus we came up with this scenario. What probably happened is they started farming in here and planting corn, and the corn is looking really good and tall relative to the farmer, thickening through time. Again, by 800, we've got a little bit of an irragric soil. By 950, we got more. But now it's getting so thick that we're not getting as good productivity in the maize or whatever food crop they're growing. By 1250, they're thinking, this really isn't working, and they're gone. Even though they after 500 years of what looks to be continuous irrigation, they pull out. Even though the canals are still functioning, even though you have peak population, even though you still have 200 more years, they must have gone somewhere else in system two. There were still other areas to farm. Now, how disruptive that was to other, farmers, there are land tenure issues to consider if all of a sudden you have one group moving within a system, but there was still irrigable land that they could have gone to. But it is interesting, right near Sadavaki, which is a large village at the time, they pull out, move somewhere else, no more irrigation deposition, flood comes in, buries it, and then the city comes in and builds on top of that. So to summarize, we have evidence of both positive and negative effects of ancient canal irrigation on soil quality. This reviews some of the positive effects. I won't read through it. I know we discussed it. I discussed it. And then the negative impacts. So it depended on where in the landscape the farming took place. It probably depended on the type of irrigation, the strategies used. Did they leave it fallow from time to time to allow water tables to adjust? We can provide evidence of both positive and negative impacts on soil quality. So do I believe that Hohokam decline was driven by soil degradation? Probably not. The impacts were variable, and again, a lot of productive land still available in the classic period. Nonetheless, that does not mean to say it was not an issue. And in some cases, it could have created extra stress that if combined with other problems, be they large floods or immigrants from outside the Phoenix Basin, I mean, there could have been things that sort of crossed a threshold. We don't know. But here I'm quoting from my colleagues, Jeff Homburg and John Sandor. What I'm arguing here really is been known for some time. We might have had soil degradation leading to some local abandonment and shifts of settlements and agricultural sites, but probably not a major driver of regional abandonment. So, yeah, where does that leave us? The good news is that ancient anthropogenic soils still occur on the landscape. And these provide us opportunities to better understand past human impacts to the environment and cultural history. The challenge is to find them, and particularly those that are still quote unquote pristine. If we do, we really should make an effort to try to characterize not just their morphology, their description, but actually obtain physical, chemical, biotic, and micromorphological properties of these soils. Really, really study them closely and compare them to areas that weren't farmed to see what were those impacts. It's important to really understand these agricultural legacies, and that's what they are. In some cases, they are a hallmark of sustained agriculture, but in other cases, maybe they indicate where the soils were overused. And this is relevant to today. Understanding these anthropogenic soils can provide insight not only to ancient farming practices, but they can also help guide efforts towards obtaining more sustainable modern farming practice in today's world where we have expanding drylands due to global climate change. Okay, I'm out of time, 7:50. So I am going to stop sharing. And
Okay, it looks like we have a couple of questions, Gary. I don't know if you want to take like a 10-second break, drink some water, and then come back.
I've got water here.
Okay. So yeah, if you click on the chat little bubble there at the bottom, you can see the questions, and you can answer them. Mary Jo, I see you raise your hand. You can put your question in the chat section, please. Thank
Okay,
you.
so I've got a question here. Does the Snaketown experience imply that the Hohokam devised a method to remove salt from irrigated soils? Um, I think that you could argue yes, that if indeed they irrigated that long, centuries, in an area that had natural salts in them, they had to have devised a way to mitigate that salt problem. Not remove it. Not they didn't completely remove the salt problem, but certainly mitigate it where they could still practice agriculture. And I think Kyle Woodson and John Sander and Colleen Stryhacker would agree that yeah, they may have fallowed fields and let water tables go back down lower and then come back and flood irrigate and wash out those salts that had accumulated. Methods beyond that, I'm not sure what they would have. See, one thing that they didn't have that, as far as we know, were drainage structures like drainage tiles. Ostensibly, they could have put in drainage canals, but I don't know what that would look like. I'm still trying to, every time I see a funny looking canal that's going away from a field back towards a river, I'm thinking, is that a drainage canal? But it's hard to show. But anyway, to get back to your question, I think, yeah, I think they did develop methods for managing those salts. Another question below that, how far from intake would fine silts be transported in low gradient canal systems? Well, the ones along the major valley bottoms, those are all pretty low gradient canals, and you can get silts accumulating pretty close to the intakes. A lot of it has to depend on how water is getting out of the main canal and deposited in the field. Generally, they're small ditches that are taking them to the individual field cells, low velocity, transporting mainly suspended loads. And so you can get those even close to the main canal head gate, such as what we found at Sky Harbor Airport. Does it appear that the Hohokam deliberately designed an engineered canal such that silts could be diverted onto rocky soils that might be improved? Yes. Yeah. I mean, that's what those silt fields, they were intentional efforts to expand irrigable area. I mean, there was water in the landscape seasonally in Cave Creek and Queen Creek and Agua Fria. And they knew that if they could build up enough of that plasma, that fine grained sediment, in those rocky soils, they could improve them enough to be suitable for growing maize and other food crops. How did they fertilize their crops over time? Okay, that's getting back to that phosphorus halo that Louise saw there. Again, we don't have any ethnographic evidence of fertilization. And because we didn't have large stock animals in pre-contact Southwest, the only real source is night soil, human excrement. And, does that phosphorus halo mean that they were using night soil? It definitely suggests some type of fertilization, and we can't think of any other source that is so phosphorus rich that could produce that. But before anyone makes a claim in print that that's what it was, one's going to need biochemical markers from the soil, and this is another thing in the future one could look at is, how did they fertilize? If you're irrigating an area for 500 years, you know, obviously the irrigation sediment has some nutrients in it, but chances are, particularly for maize, they're going to have to, I would think, bring in some other nutrients. I'm not a agronomist, but it seems like fertilization is quite plausible. The question is, what was the source of that phosphorus? What is meant by a pristine prehistoric soil? What are the indicators of changes, beneficial and otherwise, intervening since the 1300s? How much were valley soils degraded by early grazing? Okay, that's a lot packed in there. By pristine, I just mean it has not been plowed or irrigated historically. So because that's going to obviously modify both the morphology and the chemical makeup of the soil. And what are the indicators of changes beneficial and intervening since the 1300s? Well, after the 1300s, well, particularly after the mid 1400s, at least in the Salt River Valley, we don't see much evidence of irrigation until Euro-American farmers come in the late 1800s. And when they do that, it's just more irrigation sediment and shallow water tables again. But when you look at some of these soils, like the Salt River adobe, if it's 70 centimeters thick, I guarantee you only about 5 centimeters maximum is from the historic irrigation because the time depth is much, much smaller, several decades versus several centuries. And how much were valley soils degraded by early grazing? In the Salt River Valley, not much because that was mainly allocated for agriculture. But in terms of historic grazing, certainly there's debate about how much sediment was coming down the river in the late 1800s, early 1900s. When they first started measuring sediment in the river, that was a time of excessive grazing in the watershed. And so those sediment yields, those sediment loads in the Salt River historically may not be representative of when it was at Hohokam time. So that is something to consider.
Hey, Gary, there's two questions on the Q&A section by Alan Dart. I don't know if you want to answer those before you go here.
Where are they?
Q&A, it's on the same bottom panel.
Oh, yeah. All right. Let's see. Alan Dart, I know that guy. Can you elaborate on the benefits of leaving fields fallow periodically? Yeah, so if the idea is that the salinization is really driven by elevated water tables, by leaving it fallow, particularly if you're away from the main river, you want that water table to increase in depth and get down below the root zone. And then at that point, if there are salts in the soil, then you can flush them with irrigation water and remove them from the root zone. So that's the benefit of fallowing, as well as allowing maybe some nitrogen to build back up in the soil, particularly if you have certain plants, native plants growing in there that are nitrogen fixers. Alan also asked, would leaving fields fallow with naturally weedy growth help build up nutrients? Well, I guess I answered that question. Good questions, Alan. Thank you. All right. What else do we have here? Does the Salt River contain more? Oh, just shifted on me. Does the Salt River contain more or less salt concentrated seasonally? So before it was dammed, historically, salt concentrations were greatest when water flow was lowest. So particularly in early summer. All right, so the flows would peak during late winter and spring because the snow melt runoff. Probably similar for the Gila as well. So when discharges, the natural flow is heavy, salt concentration is low, but during the summer, when that discharge decreases, salt concentration increases. And of course, that's a time when they're irrigating. So yeah, it does vary seasonally. Is it possible to estimate the electrical conductivity or sodium absorption ratio values based on the archaeology? Do you have to account for adjusted values you see today during excavation? I'm not sure if I fully understand that. Based on the archaeology, the only way to really get EC is to, take bulk sediments and measure it in the lab. And then sodium absorption ratio values are based on base cations. Again, collecting the sample and taking it to the lab and measuring those base cations. So I probably didn't answer that question very well. Do you have to account for adjusted value you see today during excavation? Yeah, I'm not sure how to answer that. Another one here, were there canals down the Gila close to Gila Bend area and further down? Yeah, good question. Yes, there were canals down around Gila Bend. They have not been very well studied or documented. I have seen some canals down at Gillespie Dam, right immediately downstream from Gillespie Dam. And then some have been mapped. I can't remember if it was Frank Midville or others. I assume that they were doing where we have Hohokam, and we do have Hohokam in the Gila Bend area, that there are canals there. Now, whether or not they are still preserved is a good question, because a lot of that area, of course, is now under agriculture, and there hasn't been a lot of CRM work down there to really test if they have subsurface canals still preserved.
Okay, it looks like that's all the questions, Gary. I want to thank you and thank everybody for joining us this afternoon. We'll be back next month. We're going back to Mexico. There's going to be a lecture on the site of La Quemada in Zacatecas. I'm going to try and have this lecture up on YouTube by the end of the week if anybody wants to rewatch it or somebody couldn't join us. So thank you, everybody. Thank you, Gary. Thank you, Eric. And we'll see each other next month. Thank you.
All right. Thank you, Sebastian.
Thank you.